In this video, I'm going to introduce the equilibrium constant, or Kc for short. So in its very basic form, Kc is equal to the concentration of the products at equilibrium divided by the concentration of the reactants at equilibrium. So let's just imagine Kc was a large number. What does that mean? It means that there are more products at equilibrium. There's a higher concentration of products at equilibrium than reactants. So the equilibrium would be over to the right hand side. If Kc was very small, well, if you think about numbers in here, which way would the numbers be to get a small value for Kc? Well, the denominator would have to be bigger, and so the reactants concentration is higher than the product's concentration. So in other words, the equilibrium's on the left hand side or going in the reverse direction. And as you'll see when we start looking at calculations, these square brackets here, you can see the square brackets there, what does that stand for? It stands for the equilibrium concentrations, and that's obviously measured in moles per decimeter cubed. So this little C here stands for the equilibrium concentration. We'll go to the equation now that I've written in blue there. I've not referred to that yet. We're going to expand on this. So if you've got an equilibrium and you know the balancing numbers, so A moles of A with B moles of B in equilibrium with C of C and D of D, well, to write a Kc expression for this generic equation, it would be the equilibrium concentration of C raised to the power C. So if there's a 2 in front of there to balance the equation, you'd have a squared term there. If there was no number in front, it would just be to the power 1. That's multiplied by the equilibrium concentration of D raised to whatever the balancing number is, so raised to the power D, all over, so they're the product concentrations, all over the reactant concentrations at equilibrium. So it's the equilibrium concentration of A raised to the power A multiplied by the equilibrium concentration of B raised to the power B. So the next thing we're going to do is I'm going to put some actual equilibria on the board, and you're going to have a go at working out the Kc expression for them, and also what would the units be. So if you just remember, the square brackets stand for the equilibrium concentration in moles per decimeter cubed. So there's 3 for you to try. So what I'd like you to do is work out the Kc expression for each of those 3 equilibria, and also what would the units be of Kc. So the first one, the H2I2 2HI, so it's going to be the equilibrium concentration of the product. So square brackets, HI raised to the power 2, all over equilibrium concentration of the reactants. So it's H2 multiplied by I2. No powers here because there's no balancing numbers in front. So the next one is obviously the equilibrium concentration of N2O4 to the power 1 all over the equilibrium concentration of NO2 squared. And the last one, Kc, would be the equilibrium concentration of NH3, that's ammonia, raised to the power 2 all over the equilibrium concentration of N2 power 1 multiplied by H2 to the power 3. If we look at the units now, all you do is you take the units of concentration and whatever's happening to the square brackets in the Kc expression, you do that to the units. So we've got moles per decimeter cubed squared divided by moles per decimeter cubed times moles per decimeter cubed, which is effectively moles per decimeter cubed squared, and so these units will cancel out those units, and Kc for the blue equilibrium actually has no units. The red one, we've got moles per decimeter cubed on the top divided by moles per decimeter cubed squared on the bottom. So effectively they will cancel with one of those. So what are you left with? You're left with 1 over moles per decimeter cubed. Now we would normally take these terms up to the top, and when you do that the sign changes of the indice. So instead of 1 over moles on the bottom, it's moles to the minus 1 on the top, and instead of 1 over dm to the minus 3, it becomes dm to the plus 3. And you can see that I'm following the conventional way of writing these units. Positive powers first, so dm cubed moles to the minus 1. So we'll deal with this last one now, the most complicated one. We've got moles per decimeter cubed squared on the top, and effectively we've got 4 lots of moles per decimeter cubed on the bottom, so it's moles per decimeter cubed to the power 4. If you don't like the bracket with the way I'm doing it with the brackets, you could literally write out 4 lots of moles per decimeter cubed if you could be bothered on the bottom, and 2 on the top, and then you can see them cancelling more easily, I suppose, that way. But hopefully you're okay with these powers. So what's going to happen? Well, all of them are going to be wiped out, and that's going to go down to the power 2. So effectively this would become 1 over moles per decimeter cubed squared. So we'll deal with the squared term now. So if we square this, we're going to have 1 over moles squared decimeters would become to the minus 6. I'd lose that. And then we would take these up to the top, and the sign would change. So it would become moles to the minus 2 on the top, dm to the plus 6 on the top, and then remember we write the positive power first, so it's going to be dm to the 6 moles to the minus 2. Something that we need to know about the equilibrium constant is that it is temperature dependent, so it's only a constant if the temperature is constant. So we'll just explain that using this made up equilibrium, A plus B at equilibrium with C and D. So I've said that the enthalpy change for that forward reaction is minus 100 kilojoules per mole. So in other words, the forward reaction is exothermic, and therefore the reverse reaction is endothermic. So let's suppose we increase the temperature. What's that going to do? Well, an increase in temperature always favours the endothermic direction. So in this case, the equilibrium will shift more into the reverse, or more to the left, and so the concentration of the reactants will increase, the concentration of the products will decrease, and so if you remember, Kc is effectively a measure of products concentration over reactants. Therefore, if we're getting more of this, the reactants is increasing, the products is decreasing, therefore Kc will actually drop. If we decrease the temperature, then it's going to favour the forwards, the exothermic reaction in this case, and so we're going to have more products, fewer reactants at equilibrium, and so this number is getting bigger, this number is getting smaller, Kc will therefore increase. So we'll just finish with what's the significance of the Kc value. Kind of already mentioned this, but we'll just bring it back to the Kc expression now. So if you've got a large value for Kc, so in the order of thousands or so, remember Kc in its essence is a measure of the equilibrium concentration of products to reactants, and so if you've got a large value for Kc, You've got a higher concentration of products to reactants, so that means the equilibrium is moving in the forwards direction, and so it is lying to the right hand side. If you've got a small value for Kc, obviously the reactant concentration at equilibrium is higher than the products, and so the equilibrium's gone this way, so it's left hand side.